Strasbourg and Granada are we good to bring Jeff and Deirdre to the main room and all participants? Can anybody in Granada and Strasbourg hear me? Sorry, it's going to be a little loud. Granada.
right, apparently we are live. So good morning, good afternoon, good evening, good night, ladies and gentlemen, wherever you are, and welcome to the very first public lecture of International Space University Space Studies Program 2021. Here I am currently based in Granada, Spain. However, we have a big cohort as well watching this event on site in Strasbourg, France. And also this event is watched by 21 participants in 21 different countries as well as the YouTube audience who are following us probably in more countries. So in this special event, ladies and gentlemen, we are very privileged to host Dr. Jeffrey Hoffman, a senior, I should call spacewalker, who is also an ISU faculty member. So Dr. Hoffman is an American former NASA astronaut and currently a professor of aeronautics and astronautics at MIT in Boston. He received a Bachelor of Arts degree in astronomy from Amherst College in 1966, a master's degree in material science from Rice University in 1988, and a doctor of philosophy in astrophysics from Harvard University in 1971. And selected by NASA in January 1978 as an astronaut, Dr. Hoffman became an astronaut in August 1979. So during his career, he made 5 flights as a space shuttle astronaut, logging more than 1,200 hours and 21 million miles in space. And one of his missions was obviously the very first mission to repair the Hubble Space Telescope in 1993, when the orbiting telescope flawed optical systems was corrupted. And tonight we will have the opportunity to hear this story directly from Jeff Hoffman. So at the end of his talk, which probably will be around 55 minutes, an hour, we will open the floor up to questions. We are, as I said, in Granada, in Strasbourg, online and YouTube. So just follow the link that you will see and you can ask your questions online for Dr. Hoffman as well. Without further ado, thank you very much, Jeff, for joining us today, and over to you.
Let me unmute and tell. There we go. Yeah, always a pleasure. My career with ISU actually started with the Hubble mission because we were training for that mission at the big water tank at Huntsville, Alabama, in the Marshall Space Flight Center. This was before the current neutral buoyancy facility, huge tank, was built in Houston. So I'll be showing pictures of that later, but that was the summer that ISU met in Huntsville, Alabama, and they asked me to give a talk about, what I would be doing on this mission. And of course, as hopefully everybody knows, and you'll see more of in my lecture today, the mission was totally successful, and they asked me to come back the next summer in Barcelona to talk about what we did. And I actually hardly had to change the lecture because we did just what we said we were going to do. And you'll see some of that this evening. Anyway, I've been coming to ISU ever since, and it's always a pleasure. So with that as a brief introduction, I will share the screen and we'll get going here. And I'll put in slideshow mode. Oops, I know, hold on just a minute, I have to share sound as well. I'll be right back with you. Share sound and share. Now we're truly ready to go. Okay, so Hubble is by this time a pretty old story, although actually, given the age of a lot of our students here, some of you were very young or maybe not even alive when some of this happened. But hopefully this will give you some insight into what happened with Hubble, why we built it, what went wrong, how we fixed it. And at the very end, I'll share with you some thoughts about the significance of Hubble for our view of the universe. Actually, the story of Hubble began early in the space age. I gave the first lecture on the origins of the space age, and it was really back in the 40s when, some of the scientists in the late 40s looked at these rockets going up and thought, if we could put telescopes up above the Earth's atmosphere, we could get a much, much clearer picture of everything in the heavens. There was no such thing back then as atmospheric corrections using adaptive optics that we can do now. Still not quite as good as Hubble, but this was a dream of some far-looking astronomers. And not only when NASA finally took up the challenge to actually build a large space telescope, not only to make it optically perfect was the challenge, but telescopes on the ground, like the Great Palomar telescope here, the mirror for this was built back in the late 1940s, the 200-inch mirror. The mirror is as good as it ever was. Unfortunately, the skies over Palomar are no longer as clear as they once were. So we go elsewhere with our biggest telescopes. But the point is that telescopes don't just become unusable because their optics go bad. In fact, telescopes are continually used for decades, even centuries, because we develop more and more powerful instrumentation to put at the focus of these telescopes, better cameras, better spectroscopes and polarimeters and so on. And of course, if anything breaks with the telescope, we can fix it. This was never possible with anything that we did in space. Once you launched something, that was it. And if the next year someone came up with a better instrument, well, you just had to wait until the next satellite went up. No, Hubble, on the other hand, was not only going to contain the best optics that we could possibly produce, but it would be serviceable by spacesuited astronauts working out of the space shuttle. And remember, when Hubble was first conceived to be able to do this, the shuttle had not even flown yet. So it was a real leap of faith and imagination. And because it involved so much complex new technology, as you can imagine, it was over budget and behind schedule. There was a lot of criticism. It was a lot more expensive than originally anticipated. But finally, in the spring of 1990, it was launched on the Space Shuttle Discovery. And I'm not telling this as a suspense story, okay? Hopefully, even those of you who don't remember this in person know roughly the story that when they first started to commission Hubble and work the focus back and forth to find the sweet spot, this was about the best it could do. Hubble could not focus properly. It had what is known as spherical aberration, something that's familiar to a lot of amateur astronomy mirror makers. But who would have imagined that this could happen with a billion-dollar telescope made, for NASA by one of the, premier optics manufacturers of the world? It was a disaster. And again, if you didn't live through that time, you may not fully appreciate what a disaster it was, both for NASA, for the astronomical community. That was the time, the early 90s, NASA was trying to convince Congress to put up the initial funding to start work on the International Space Station. And believe me, NASA was not popular in Congress at that time. And in fact, the message that was coming out loud and clear was, show us what you can do about Hubble and then come back and talk about the about the space station. So what are we going to do? Well, if you're going to solve a problem, the first thing you have to do is figure out what caused the problem. Why is my slide not advancing here? Let me try. There we go. So, basically the Hubble Space Telescope uses it's a reflecting telescope. I won't get into the details of Ritchie-Chrétien objects, but basically light is bounced off a primary mirror, which has a specific curvature, and then, reflected off a secondary mirror through a hole in the primary mirror. And then you have cameras and other instruments behind it, each of which stick a little pickoff mirror at 45 degrees to divert the light into their part of the light into their instrument to actually make the observations. So that's, here you see a current version of Hubble. So, the mirror is kind of here, and this is just the empty space. The secondary mirror is up here, and then all the instruments are in this back section, which is what makes Hubble actually function. And this is the high gain antenna to a KU band antenna to get the data back up to a tracking data relay satellite. How do you make a telescope? Well, the Hubble Space Telescope was designed to bring into space the advanced telescope technology of the mid-20th century. Like the Palomar mirror, the Hubble mirror was made out of a big chunk of glass. You start out with a very flat piece of glass, and then you have to machine it to just the right shape so that, and you're polishing it here, so that no matter where in the mirror the light hits, whether it's at the very outside or the inside, it all gets focused to the very same point. And that's why getting the curve of the mirror, if this were just a sphere, then you would have a spherical aberration where the rays hitting the outside would not be focused at the same place as the rays hitting the inside. So measuring how you make this mirror, while you're making it, measuring the shape becomes critical. And I'm not going to go into the details of the optical measuring device, but the key part of it was what they call this measuring rod, which essentially ensured that all the optics in the measuring device, in other words, the device that would ensure that you were getting the right shape out of the mirror as you ground it, it had to be placed at exactly the right position with respect to the focal point of the mirror. In order to do that, this is the top of that measuring rod. And by the way, this is the actual reason for the error is something that even a lot of professional astronomers don't quite know the reason. So I'm sharing this with all of you. It's really an object lesson. They wanted to put this cap over the top of that measuring rod, and then they would shine a light through this hole, which you can see with the arrow here. And that light would then bounce off the top of the measuring rod, and you could then determine the height using the light. Now, they didn't want the light to bounce off this cap itself, so they covered the cap with an anti-reflective coating. Well, during the investigation, in one of the closets at the old Perkin-Elmer factory where this mirror was made, they actually found this measuring rod and the end cap. And lo and behold, some of that anti-reflective coating had peeled away, and actually the area there is bigger than the area of that hole. And so when the light was shining down on it, instead of reflecting off the top of the measuring rod, most of the light was reflected off this cap, with the result, here's the cap. This is what was supposed to happen, and they would be able to determine the height of this. But instead, as I said, the light reflected mostly off the cap. And so the actual measuring rod was 1.3 millimeters too close to the mirror, and that made all the difference. Doesn't sound like a lot, but you're dealing with very precise optics, so that when the mirror was finally made, and it was smooth to a fraction of the wavelength of light, that was the big challenge. There was some question of whether they should do a big end-to-end test, but we were already behind schedule, over budget, and in any case, an end-to-end test was not done. And the result of the misplacement of that measuring rod by 1.3 millimeters meant that when it was determining the final shape of the mirror was slightly too flat. So the original shape of the mirror would have gotten rid of all spherical aberration, but about a little between 1 and 2 microns, too much glass was removed from the outer part of the mirror. And so it was slightly too flat and reintroduced some of that spherical aberration. By the way, the average human hair is about 50 microns thick. So we're talking about a very, very small amount of glass, that extra glass that was removed. But as I said, these are ultra precise optics, and that made all the difference. So how are we going to fix it? Now we know what the problem is. Well, as I said, you get the light comes through the hole in the primary mirror, and each instrument has a little pick-off mirror, which picks off part of that beam and reflects it into the instrument where it's used for whatever that instrument does. Here's what was finally developed. And, you know, I can't give enough credit to the optical engineers, the mechanical engineers, the electrical engineers who put all of this together. So here's what we basically did. We have to block the out of focus light beam from getting into each of those mirrors. Instead, reflect it up to a second mirror, and each of these extra mirrors are about the size of your thumbnail. And that mirror has a slight curvature in it to correct for the flatness of the original primary mirror. And then that light gets reflected into the scientific instrument. If you can actually, if you're going to build a new instrument on the ground, you build this correction into it, no problem. But, and we actually were taking one instrument out of the Hubble and replacing it with a new wide field planetary camera #2, which had this built into it. But there were several other instruments, actually 4 other instruments in the telescope for which we had no replacements. And is there some way that we could put all of these little mirrors in just the right place to be able to use those instruments? Well, to do that, we had to sacrifice one instrument. We took it out, and what was put in place was, this was in one of those big instrument containers. By the end of the final Hubble servicing mission, and we've serviced it 5 times, all of the new instruments that were put in had this correction built in. And so they brought back this corrective optics apparatus that we had installed, and it's now in a place of honor in the Hubble exhibit in the Smithsonian Air and Space Museum. I don't know what the current status is, but I took this picture when I was there the last time. You can see, quite complicated, lots of mirrors and levers and folding arms. So as I say, the mechanical engineering, the electrical and optical engineering, just extraordinary. All right, now from an astronaut's point of view, we know how to fix Hubble. Who's going to do it? And as you can imagine, this was considered a pretty prime assignment within the office. It was also recognized how critical it was, and anything that NASA could do to reduce the risk of failure, they were going to do, including the determination that if you're going to be one of the spacewalkers to fix this, you need to have already done a spacewalk. Well, none of my first 3 flights had spacewalks assigned to them, but it turns out that on my very first flight, I ended up performing the very first totally unplanned contingency spacewalk in NASA history in order to attach these 2 apparatus on the end of the robotic arm so that the next day we could fly up next to a satellite, which we had recently deployed, but which hadn't turned on, and use these to flick the electronic switch on the outside of the satellite, hopefully to turn it on. So I was a recognized EVA crew and was fortunate enough in the end to get onto this mission together with spacewalkers, my partner, Story Musgrave, and then Tom Akers and Kathy Thornton were the other team. There were so many, it wasn't just the optics that had to be fixed on Hubble. It was we had to replace the solar panels. There was a tape recorder needed fixing, circuit breakers needed replacement. There were about a dozen different things which we had to do. And it was going to take 5 days of walking. NASA had never, ever done 5 spacewalks in one shuttle mission. And this mission was limited to 11 days just because of the consumables we have on board. And so there was no time to rest between the spacewalking days. And it was decided that it would be safer to have 2 teams of spacewalkers. I was on the team that went out on days 1, 3, and 5. Tom and Kathy went out on days 2 and 4. And that meant, tremendous amount of training because, as you can imagine, the pressure was on. This is the training for the Swiss astronaut Claude Nicollier. He's a European Space Agency astronaut, and Europe had paid for 15% of the telescope. So this was their part in the repair mission. This is a Hubble-shaped helium balloon, which is being manipulated by this arm in the simulator area. We were the first crew to make full use of virtual reality during our training, but the majority of the training for the spacewalks takes place in the water tank. There I am getting ready. Now, this is, as I said, we were in Huntsville, Alabama. We would go there for a week at a time and go underwater every day. Again, we would alternate. The pool was 50 feet deep, but we still had to break Hubble into 2 pieces because it's so big. And for those of you who know something about diving, we would spend 6 to 8 hours down around 40 feet. They had to actually introduce a nitrox system for our underwater training, which had never been done before. But the purpose of this is to test out all our procedures and get practice so that we know exactly what tools we're going to need, where we should position ourselves. Because again, we, up in the space station now, the other day, they had allocated 2 spacewalks to install a new solar array, and they didn't get the job done at the end of the second day. Something went wrong with one of the spacesuits, but other things can happen too. So they went out a third day, big deal. Well, we didn't have that luxury. So we really needed to increase our efficiency to the maximum possible. So we spent a total of about 400 hours underwater in training for this mission. And we spent a lot of time at the Goddard Space Flight Center, where they actually were putting together the new instrument, and they had very high fidelity simulators. Yeah, we like to see the instruments that we're going to be installing. This is a new camera. And because of course, what we use underwater is not the real thing. And so in your mind, when you're in the water, you have to imagine what the real thing looks like. They try to make it as realistic as possible. But anyway, after a year of training, very intense training, we got in our T-38 jets. We fly down to Kennedy Space Center. You can see our shuttle on the launch pad. The night before launch, our launch was delayed 1 day. We got in and got ready to go on the 1st of December, but the winds were too high. That night, there had been a total eclipse of the moon, which I viewed as an omen. Also, my second flight, which I had done back in December of 1990, we had launched on December 2nd. So I thought, December the 2nd is a good day. And sure enough, on December the 2nd, we lit the fire. on our way up into orbit, and 8.5 minutes later, we are up at the highest that the shuttle ever goes. We put the Hubble telescope up around 600 kilometers to minimize atmospheric disturbance. Once we're there, no time. Everybody on the crew had flown before, so we all knew what we were getting into. We didn't need the kind of accommodation time that most first-time flyers often take. In the airlock, where we normally store 2 spacesuits, we now had to store 4 spacesuits because we were all different sizes. And so just unpacking took quite a bit of time. And all of the equipment is packed in protective foam boxes like this, because you've got to protect everything against launch vibrations. Tools are absolutely critical to what we can do. Remember, we're working in bulky spacesuits with big, thick gloves, but the tools that we were given were what made this possible. We had about 200 different tools on board, of which we planned to use maybe 50 of them, and all the rest were backup, because we were ready for all sorts of contingencies, which we had thought about and practiced, and then all the unknown unknowns. Who knows what might come up. So then we have to, the night before the first spacewalk, after we've actually rendezvoused with Hubble, and that takes a couple of days. So remember, the clock is ticking. So now we do the checkout of the spacesuits. Remember, a spacesuit is like a miniature spacecraft. It's got to provide all your life support, all your communication, your thermal control, your oxygen, pressure, and so on. You don't want to go out with a spacesuit that you don't have 100% confidence in. I'm putting in the back of the backpack. We have to, every day, we have to put in fresh batteries, carbon dioxide scrubbers. This is the second flight where I launched on the 2nd of December, as I said, and my wife's birthday happens to be on the 5th of December. So for the second time in 4 years, I was missing her birthday, but we celebrated from space, and the whole crew sang happy birthday. So you can't forget about your family and friends while you're up in orbit. But back to business. Here's how you get ready for a spacewalk. We get up early in the morning. I eat as big a breakfast as I can, because I know I'm not going to get anything to eat for the next 8 hours or so. We put on radiation monitors. Remember, we're up high now, close to the inner Van Allen radiation belts. We got about 10 times the normal shuttle dose. Still nothing to to worry about, but they did want to monitor us, as well as heart monitors. It can get very cold at night, so we wear long underwear, like when you go skiing in the winter, although it's made of Nomex, which is flame retardant. The yellow thing that you see there is what we call a UCD, or urine collection device. When the women couldn't use this, so that's when they developed the super absorbent diapers, but I was kind of a traditionalist, so that's what I did. Now, as I said, it can get very cold in the shade, but it can get very hot in the sun. And so over the thermal underwear, we wear the cooling garment, which has many meters of tubing going through it, through which we can pump cold water as much as we may need for however, if we're feeling too hot. Then when you get everything, you're already there, you slide into your trousers, which you can do 2 legs at a time up in space since you're floating, and then into the airlock, where the upper part of the spacesuit is hanging on the wall. It's a real squeeze to get in there, and once you're in, it is a great satisfaction. So the spacesuit operates at about 0.3 of an atmosphere in pure oxygen. A spacesuit is like you think of it as an anthropomorphic balloon. And if you've ever played with those long, thin party balloons, you know that when you try to bend them, they want to snap back. Well, so does a spacesuit. You know, your fingers want to straighten out, your arms want to straighten out. And the higher the pressure in the suit, the stiffer it becomes. So we want the pressure to be as low as possible. But of course, we need enough oxygen to be able to function. But we don't, for a short amount of time at least, we don't need the nitrogen. So it's pure oxygen at 0.3 of an atmosphere. But if you go from 1 atmosphere down to 0.3 of an atmosphere, all of a sudden, and divers again will understand this, you'll get the bends, decompression sickness, nitrogen bubbles will form in your blood. So we actually don't start at 1 atmosphere. We take the cabin pressure the day before we start our spacewalks down to about 2/3 of an atmosphere. And of course, we increase the oxygen percentage so that we don't get hypoxic. And at that point, before going out on a spacewalk, we have to now breathe pure oxygen for 40 minutes, 40 minutes. And that gets enough of the residual nitrogen out of our blood that we can then take the spacesuits down to 0.3 of an atmosphere without fear of getting the bends. Well, you all know that we did succeed. As I said, this is not a suspense story, but at the time, we didn't know at all whether it was all going to work. And we went through 5 days of very intense spacewalking. At one point, I had just installed this white thing as the radiator for the new camera. This is the old camera, which we had just taken out, and we suspended over the side of the shuttle in temporary stowage. This is the box that it came in, that the new one came in with thermal insulation. Once we get that in, the ground now wants to conduct some tests to make sure that it's properly connected. And that meant that we had about 5 or 10 minutes when we had nothing. We were basically waiting, because if there had been a problem, we would have had to go back there and redo the connections or try to fix whatever was wrong. In any case, that gave me a few minutes. Very, very rare to have free time on a spacewalk, but I asked the Claude, the arm operator, to drive me out over the wing so I could use my trusty Hasselblad and take this picture of what it's like being out to service Hubble. There's my partner's story. This is the telescope. It's very wide angle, so the Earth is not really flat. Trust me on that. We went around it every 95 minutes. And by the way, it was 95 minutes because we were in a higher orbit. When you do your orbital mechanics and you learn about Kepler's laws, you'll know that the higher your orbit, the slower you go and the longer is the period. So yeah, we did not have the normal 16 sunrises and sunsets every day. We only had 15. But I'll tell you, when the sun rises or the sun sets, sometimes you just have to stop for a minute and take in the view, because it's absolutely awe-inspiring. Here we are in the early morning light. And this is an astronaut's view of the Hubble telescope. It's about 15 meters from top to bottom, but it looks much bigger when you're actually at the bottom looking up, I have to say. The top of the telescope has magnetometers. These bars you see here are electromagnets. We don't have thrusters on the telescope. They're controlled by control moment gyros, which I talked about in the material science lectures. But you sometimes have to be able to dump momentum of those flywheels. So you need something that's rigid. And we don't have thrusters because of contamination. So they activate these electromagnets, which interact with the Earth's magnetic field. And that allows you to change the speed of the control moment gyro without disturbing the telescope's pointing. But to do that, you need good magnetometers. Well, they put 2 up there, and they were so good that, they're never going to fail. And anyway, we have 2 of them. So they didn't design them to be removable and replaceable. And wouldn't you know, both of them failed in the first couple of years. So we had to go up and put new magnetometers on top of the old ones, and then remove the electrical connectors from the old ones and connect up the new ones. And that meant that 2 different times we went way up to the top of the telescope, and no place if you have a sense of vertigo. It's a long way down, I'll tell you. But those were some of the most extraordinary moments of my life. I'm the one in the red stripe there. And that day's story was locked, his feet were locked onto the end of the arm, and I was floating free. Of course, I was attached by we all have our tether cords, a stainless steel cord. But nevertheless, I felt like I was just an independent satellite floating in space, just a memory that will be with me for my whole life. Anyway, everything they asked us to do, we did, and some other things as well. We had a few problems. When I opened up these big doors to replace the gyroscopes, I couldn't get them closed. They didn't close properly, and that took us an extra hour to figure out. We had to make an unplanned use of one of our special tools to do that. One of the old solar arrays didn't fold up properly. We had to toss it overboard instead of bringing it back. These are new solar arrays, which we installed, and all the new instruments and circuit breakers and tape recorders, everything we were supposed to do, we did. And so we were a very happy crew when we came back, and it was a nice holiday season for everybody. We got back the 13th of December, 11 days after we launched, and it was great. But we didn't know, we had done everything that we were asked to do. We put in the corrective optics. Now, as I say, this is not a suspense story for all of you, but it was for us. Were those corrective optics going to work? And the thing is, you cannot turn on most of those instruments right away because you have to allow enough time for them to outgas. Otherwise, when you turn on high voltages, you'll get sparks, which would be a disaster. So it wasn't until just before New Year's that they actually turned on the instruments and started collecting images. And I'll never forget that moment. It was about 1 o'clock in the morning, 1994, January 1st. I got a phone call. I was just cleaning up from our party. It was an old astronomer friend of mine working at the Hubble Space Telescope Science Institute in Baltimore. Hey, Jeff, Happy New Year. Happy New Year, I said. He said, do you have any champagne handy? Well, yeah, we still had a half a bottle in the refrigerator. He said, pour yourself a glass. We just got the first images from Hubble, and it works, as everybody knows. And despite the fact that this isn't a suspense story, when I give this lecture in public, somehow people still applaud when I show this picture. But the impact has just been extraordinary, what Hubble has done for our view of the universe. These iconic images, which have almost become cliches, but the idea that we can view the birth of stars and the death of stars in these planetary nebula, which look like the work of some psychedelic artist, and yet this is our universe, things that we're discovering that exist out there, which are just mind-boggling. But, so many discoveries Hubble has made. And, there have been week-long scientific conferences devoted to Hubble results. So I'm not going to even try to give even an overview. I'm just going to choose the one area where I think Hubble may have made the biggest contribution to our current view of the universe. And by the way, one of the great things that the Hubble project has done is that all of these images can be downloaded free anywhere in the world. So take advantage of that. But anyway, Einstein's theory of general relativity that mass has gravity, which can bend space. And so when light from a distant object passes by a galaxy or cluster of galaxies, it's bent, and you actually see a false image. Or if it's totally cylindrically symmetric, you see what's called an Einstein ring. So this ring here is the blurred out image of a far away galaxy or quasar that's going by this nearby, much nearer a galaxy. And by analyzing this, you can determine the amount of gravitation from this interior object, which turns out to be something that astronomers had suspected for a long time, by studying the dynamics of stars in galaxies, but this was an alternative proof that the gravity that we can measure is about 5 times greater than we can account for by the stars that we can see. And so we've come to believe that every galaxy, almost every galaxy at least, is surrounded by a halo of dark matter. Dark matter which has gravitational attraction, but we can't see it. It doesn't seem to interact with electromagnetic radiation. We don't know what it is. We know where it is. We don't know what it is. And 4/5 of the gravity in the universe is determined by this dark matter. It keeps our galaxies together. Also, going back into the early 20th century, Edwin Hubble, for whom the Hubble telescope is named, was able, using the 100-inch Mount Wilson Observatory, to measure both the distance and the radial velocity of many galaxies. And he found that on the average, most galaxies seem to be moving away from us. You look at the Doppler shift. Not only that, but the farther away they are, the faster they're moving away from us in almost a linear sense, as though if you turn the clock around and extrapolate backwards, as though everything started and from a minute point and then just expanded. This is, of course, the theory of the Big Bang. The actual nature of the Big Bang is beyond our physics at the moment. But one thing we do know, when you take all of the gravitational mass in the universe, the regular matter, the dark matter, its effect on all of these expanding galaxies should be to gradually slow down this expansion, right? And we want to, and of course, we would like to measure the rate at which this expansion is slowing down. And it turns out that the farther away a galaxy is, the more accurately you can make this measurement. And Hubble now, with the corrective optics, had the capability of resolving these faraway galaxies, measuring their redshift, and we can actually do these determinations. There were 2 independent groups who were given the task of doing this measurement and doing the calculation. And for a long time, we heard nothing from them. What's going on? Well, they finally got together, and the reason they hadn't published was because the results they were getting were absolutely unanticipated. And could we be making a huge mistake? And if we announce this, our careers will be ruined. But no, both groups came up with the same conclusion. The expansion of the universe is not slowing down, it's accelerating. So there must be something else going on here besides just gravity. And we've given it a name. It's called dark energy, which opposes gravity and is speeding up the expansion. And it's great to give it a name because it makes it sound like you know what you're talking about. But in fact, we don't have a clue what dark energy really is. But using data from the microwave background collected by other telescopes, we can determine that dark energy makes up almost 75% of the universe. And this dark matter makes up another 23%, more or less. So where are we? Over 95% of the universe, we don't know what it is. And everything that, I'm sorry for this, students, but I have to tell you, everything that you've studied in physics, chemistry, and so on applies to about 4% of our universe. But look, don't get discouraged. This is what makes science exciting. Every time you make new discoveries, new questions arise. And, the search for what this dark energy is and the dark matter, this is going to be, could lead to some fascinating new physics. Who knows where it's all taking us. We hope that the next great telescope, the Webb Space Telescope, which like the Hubble telescope is using new technology. Now we've gone beyond the single mirror of the mid-20th century, and we're getting ready to send into space the advanced segmented optics where you have multi-mirror telescopes. And we're going to, and this was developed in the latter part of the 20th century. And this is not going to be orbiting the Earth. It's going to be 1,000,000 miles away, and it will be looking at light from faraway galaxies, redshifted so much that this is basically an infrared telescope, which has to be kept cool. So we have these 5 enormous sunshades. And to give you an idea of the scale, there's a person, and there's the mirror before it was finally folded up. This is at that test area at Goddard that I showed you pictures of before. This will give you a sense of scale of the whole thing. Those sunshades are roughly the size of a tennis court. They've all got to be folded up, and the telescope has to be folded up so it can fit under the shroud of an Ariane 5, which is hopefully going to launch it late next year is what we're looking at now. So cross your fingers. It's not going to be serviceable, and we're going to have a lot of white knuckles while all those sun shields are opening up. Here it was folded up before being packed up, and we'll just wait and see. In the meantime, you may have heard Hubble is having some computer problems, and its payload computer is currently down, so it's not conducting observations. They do have a backup computer. Hopefully they'll get it working again. Unfortunately, without the space shuttle, we currently do not have the sort of repair capability to go up and replace those computers that we once had. Let's hope they can get it fixed, because it would be great to have the Webb telescope and the Hubble telescope. Remember, Hubble can even go into the near ultraviolet, and so they would be great complementary to one another. In any case, that's the story of the initial part of the Hubble Space Telescope. If I had another hour, I'd remind you about the other 4 servicing missions and how they've continually increased Hubble's ability to observe the universe to the point where it's now over 1,000 times more sensitive than it was when we first went up to service it. And that's the great value of servicing. Sure, it's great to be able to fix things if they break, but even if they don't break, you continually develop new and better instruments that you can use with this incredibly precise now optics. And so let's hope the story of Hubble goes on. I've been very fortunate to have played a not insignificant role in it, and I still love looking at the images as they come down from Hubble, and have the warm feeling that, you know, I helped make it happen. And it's always a pleasure to share the story with interested listeners like all of you. And with that, I'm going to turn it back to the TAs. I'll stop sharing, and we'll look forward to about a half hour of questions.
Thank you very much, Jeff. That was an amazing and without doubt quite an exciting session. So without further ado, we have a bunch of questions for you.
Well, I hope I have some answers. I do not have any more information. They're troubleshooting. You know, typically, you know, I'm not formally connected with the Hubble program. I try to follow it as closely as possible, but we'll just have to rely on the public news.
Did you experience any sort of acrophobia?
Yeah, or vertigo, as I mentioned. There have been, some astronauts have mentioned a sense of vertigo. I did not feel vertigo. And on my first spacewalk, I was always close to the shuttle, and I was holding on to the shuttle. So I never felt, you know, like I was falling or something. What was very interesting, that picture I showed you where I was floating up at the top of Hubble, where we're a long way from the shuttle, I decided that, you know, when I first went up there, I wanted to let go just to see what it would feel like, because as long as you're holding on to the shuttle is so much more massive. And it's the same thing with the space station. Um, so, you push and pull on it and you feel yourself moving, and the shuttle is your point of reference, or the space station, where whatever you happen to be holding on to, because it's much more massive than you. I said, all right, I'm just going to let go and see what it feels like. And the first time I went to let go, I realized that I had not let go. So there was something deep inside me that was saying, hey, stupid, you're 600 kilometers above the earth. Don't let go. And then I said, well, okay, I know my physics. I'm not going to fall. So I let go. And sure enough, I didn't have a feeling of acrophobia or vertigo. What I mentioned briefly was I psychologically transformed into an independent satellite, independent of the shuttle. And what I really enjoyed, and of course, remember, I'm connected by a stainless steel cable, so I'm not floating away. I was very careful not to push myself when I let go, but I could turn myself so that I couldn't see the shuttle. And I'll never forget just floating during the nighttime, just looking up there, and I was floating. And again, this was totally weightless. I'm on that short amount of time, I don't experience atmospheric drag or gravity gradients. So gravity was the only force acting on me, and I truly was a satellite. So that's my experience, but you ask another astronaut, and you'll probably hear something very different. Um, I think it's very important, and I constantly had to remind myself, keep a little bit of my consciousness. You have to really be concentrated on your work, okay? We don't want to mess up Hubble, but keep a little bit of my consciousness just to appreciate this extraordinary environment that I'm in. Floating 600 kilometers above the earth doesn't happen every day. So I was very fortunate. And by the way, talking about itches, I talked about the pressure difference. When you drop from cabin pressure to 0.3 of an atmosphere in the spacesuit. Well, when you get back into the airlock and you repressurize, it goes up. And just like when you dive, sometimes you have to pinch your nose in order to equalize. Well, you can't pinch your nose when you do a spacewalk anymore. Then you can scratch it if you get an itch. So what they do, if you request it, they put a little like a cube, a 2 centimeter side cube of foam rubber in sort of the lower left corner of my helmet. And if I needed to, I could then push my nose into that, and that effectively blocked up my nose, and I could do a Valsalva equalization as the pressure increased. And it had the secondary purpose that if your nose did start to itch, you could just push your nose down into that foam rubber and scratch it.
Thank you very much, Jeff. Moving on to the next question. If fixing operations didn't solve the problem, do you think it would have been a further attempt? If so, what could have been possible?
Well, we could not have done any more spacewalks, okay? But on the second Hubble servicing mission, I was at that point the EVA Capcom. So I was talking to the people up there, and they found that some of the insulation on the outside of the telescope, which had been in good shape when we were there, this was now a little over 3 years later in the, actually, 4 years later in February of 97, I guess it was. They didn't know exactly what to do. So we actually came up with a way that they could, do a temporary repair. And then on every further servicing mission, they brought up extra insulation. So you can't, for a shuttle mission, we were limited in the number of spacewalks we could do, unlike the situation on the space station today. But if there was something that turned up in one mission, and we knew that another mission was being planned, as in the sense I just talked about, you could accommodate in that way.
Thank you. Have you had a moment during the repair when you felt like your heart stopped because you thought that something was not going according to plan, or because you thought you made a mistake? Please tell
Yeah, I
us.
mean, as I mentioned, when the very first thing that we did, we were certainly, we knew how complex Hubble was. We knew that there was a high probability that something was going to go wrong. But hopefully you get pretty well into the mission before you start having difficulties. Okay, the very first task that we had was to open the big doors and replace two of the control of the gyroscopic units, not the control moment gyros, but the gyro sensing units. It was very complex. We had developed a new procedure to do it where I would basically push Story underneath inside so that his head was inside the telescope, and I would unbolt them and he would remove it. I would give him the new one. He'd hold it in place. I'd do up the bolts, and we demonstrated that we could do it. And it went perfectly up there. Story went off to do another job. And all I had to do was to close the doors. And basically there are three latches on the doors. There's one in the middle, which is kind of like a door handle. And that's the first one that you close. And then up at the top and the bottom, there are extra latches to hold the door really tight. So I closed the door like I had done many times underwater, went up to the top to close the top latch, and it wouldn't fit, wouldn't close. I won't say my heart stopped, and luckily my microphone was not hot at the time. I won't tell you everything that went through my mind at the time, but it wasn't pretty because this was the very first task. And this is a major catastrophe. If we can't get the doors closed, we lose the telescope thermally and because light leaks into it. So, here's where having people, astronauts, I suspect if, putting in those gyroscopes, you could imagine, maybe a clever robot could have done it, but, we sent lots of pictures of what was going on. I went to the bottom latch. I said, well, I'll do maybe I'll do the latches first and then I'll do the middle latch. No, that didn't work. And it took me about probably half an hour to really figure out that the door somehow had warped, and it was going to take two of us. One, we'd close the center latch, and then I'd go up at the top and push the top closed, and then I could actually do the latch. But Story would have to be at the bottom pushing at the same time, and then we could get the door closed. Problem, Story was free floating that day. I was standing on the end of the robotic arm, so I could push and react that force against the arm. And so I could, the robotic arm. So with one hand, I could push, and the other hand, I could flip and close the latch. Story, on the other hand, was free floating. We had no time to attach a foot restraint or anything. We didn't have any available. We had not planned on doing that. So with one hand, he stabilized himself. With his second hand, he pushed the latch. He could push on the door. And with his third hand, if he had had one, he could have closed the latch. But he only had two hands. So that didn't work. And we were getting, we sent lots of pictures down to the ground, but the situational awareness that you have when you're on the spot is just so much better than anything you get just from a picture, no matter how good the pictures are, because the ground kept coming up with solutions which I didn't think were going to work, and we tried it, and sure enough, they didn't work. We finally came up with the idea. We have a ratcheting device with one of those big nylon straps that you can ratchet to hold things down, and that's actually why we fly it. If we have a payload and somehow the latches don't work, we can use this device, and it can exert up to about maybe 4,000 newtons of force. And we were just going to wrap it lightly around two fixtures on the door that we could use, and Story could both hold onto that and ratchet it tight. And once the door got tight, then he'd be able to close the latch. Somehow or other, on the ground, they got the idea that we were going to wrap this around the entire telescope and then tighten it. And I think they had visions of the telescope collapsing like an aluminum beer can that you squeeze on. And so they didn't want us to do it. And we said, well, this is the only thing we can think of. And in the meantime, my electricity, my battery was running low, and we were running out of time. And finally, that was the call of the flight director, Milt Heflin. That's his job. He said, all right, people, decision time. They obviously, Story and Jeff have a better idea of what's going on up there than we do. And we just got to trust them. They're not going to break the telescope. So go to it, guys. And we did it, and it worked. And so Hubble lived to tell the tale. So, yeah, that was the most heart-stopping moment for sure.
Thank you, Julia, for this amazing question. Moving on. We have, if fixing operations didn't solve the problem, do you think it would have further
No, we just had that question.
Oh, yes, sorry. I think someone posted it again. Okay. On one pic, we can see a virtual reality headset, a technology that was very ahead of its time. It
was, they had actually, NASA Johnson Space Center had established a virtual reality laboratory, and I was always interested in VR. So I went to see it one day, and the guy who ran the lab, when he knew that I was on the Hubble crew, so he said, "Hey, we got a model of the Hubble telescope. Would you like to see it?" And I looked at it, and I realized, we spend time in the water tank so that we can get all of our positions, and we practice doing things. But and of course it's time in the water is a lot less expensive and precious than time in space. But nevertheless, it's expensive to run a water tank. And it seemed to me that there were certain things we could do in terms of positioning ourselves, even though, this was VR where the update rate was about once per second. Okay. So if you moved your head too fast, the scene didn't keep up with you. But luckily, when you're in a spacesuit, you want to move very slowly because you're moving these massive objects around, and they're very delicate, and so you don't want things to be moving very fast. And so I found if I trained myself to move my head very slowly, it worked really well. So yeah, before we would go into the water, very often we had a model of the arm, and we would somebody would get on the arm, and is it better to approach it from the right or the left, and how high do I want to be? And so we would work all that out in virtual reality, and we didn't have to waste time in the water doing things that we could actually practice using our hands and doing things in the water that we could not do in virtual reality. Now, of course, the virtual reality capabilities are far, far more advanced, and it's a regular part of crew training for many aspects of space flight. We often, the typical a day when we would be doing a water tank run, we actually had a physical 3D model of Hubble, about a meter top to bottom. And we would go over exactly what we were planning to do that day. And we had a model of the arm, and it would be sitting in a model of the shuttle's payload bay. And virtual reality back then had its limitations. So we also used a real physical 3D model for our training.
Thank you. Thank you, Guillaume, for the question. Considering the recent problems with Hubble, would this be an argument to design a new service, spacecraft again? Do you think we need?
Well, I think the first thing to do, I can't really talk about Hubble. I mean, if for some reason it turns out that Hubble really has failed in a way that even with the backup computer, they can't recover. And if it turns out that this might be something that's amenable to robotic servicing, I know the people at Goddard, our Space Flight Center, they're working very hard on developing robotic servicing capabilities. And that probably could be done quicker than developing new human capabilities. Because right now, we're flying in capsules. The shuttle was a superb platform for doing spacewalks. We could carry the tools. We had the robotic arm, and all those things. So we'll just have to see. I hope new servicing is not necessary. I'm sure it's something that if it did become necessary, we would start thinking about it and see if it's within the bounds of our current robotic capabilities.
Thank you.
And as I said, the Webb telescope is not designed for servicing, period. It's going to be a million miles out beyond the orbit of the moon. And right now we don't have the capability of sending people out there. And on the other hand, again, if something goes wrong, God forbid, with the deployment of the Webb telescope, you can bet people are going to start thinking first about a robotic servicing mission. And if that is not possible, we've invested a lot of money into the Webb telescope, and I suspect we would do anything that's possible to try to fix it.
Thank you. Moving on, do you think it was a mistake to scrape the shuttle program?
Well, I wouldn't say the shuttle program was scrapped, because the shuttle for 30 years, let's remember, 3 decades, the space shuttle was the space program of the United States and most of the Western world. And hey, the shuttle was designed a long time ago. At one time, before the Columbia accident, yes, it was, people thought, yeah, we could just keep upgrading the shuttle, and sort of like the DC-3s, they still have DC-3s that are flying with proper maintenance. And the shuttle would be used to transport people and material to the International Space Station. That's really how the station was designed, for continued shuttle servicing. But after Columbia, the thoughts changed. The shuttle really was getting old. It was becoming more and more expensive to operate safely and more difficult to operate safely. We managed to operate it safely for the remainder of the construction period of the International Space Station. But I think it was the right decision that, the shuttle has lived a useful life. Let's build the next generation to service the space station, which was what NASA tried to do with the Constellation program. I think the great tragedy is that, we knew the shuttle was going to be retired back in 2004, and were not able to build a replacement during those 7 years. So that was the big mistake. Thank you.
Next, we have a question asking, do you think that all future space telescopes should be serviceable? RST, GWST, etc. Should there be any limitations on serviceability?
Well, as I said, let's not talk about repairing. Let's assume that the Webb telescope deploys and everything goes just fine. The instruments that it has to observe the universe are the instruments that are built into it now. When Hubble was launched, it had early 1970s type instrumentation, because it was designed early, or at the very latest, things that came from the 1980s, but really it was 1970s instrumentation. Now it's a 21st century telescope. On the other hand, the instruments that the Webb telescope has are excellent. The Chandra X-ray telescope, the European X-ray telescope, they are not serviceable. They're not in serviceable orbits. But they're still turning out first-class science, and I'm sure the Webb telescope will for its entire life. But you do give up something without serviceability, whether it's robotic or human. And actually, as far as the way I think serviceability should be treated, I think that telescopes and many other satellites really should be designed for robotic servicing. And frankly, it's harder in many ways to design for robotic servicing because at least our current robotic technology doesn't have the same level of responsiveness and that humans do. And so if you can design a system that can be serviced by robots, if something seriously goes wrong that's beyond the capability of the robots, at least if you then go after it with human servicing, you're starting with basically a much simpler system than some of the complex things that you would run into in satellites that are not designed for servicing. So that's my hope for the future of servicing, and I know that's the hope for the groups at Goddard and other places that are thinking about satellite servicing. It does require that if you want to take advantage of servicing, then you need to incorporate that into your satellite when you design it. And it's a little like the chicken and the egg problem, because the people designing the satellites say, well, we're currently not doing servicing, so why should I go to the trouble of making it compatible? And the people who would like to design, send up a robotic servicing mission say, well, we can't really do it unless you make your telescopes or satellites compatible. So it's in early days, but I suspect that the economic benefits of servicing, particularly out at geostationary orbit, where the satellites up there are worth a lot of money, that's what's ultimately going to drive servicing. So something for all of you to be looking out for over the next decades.
Thank you, Jeff. Next, we have a question that asks, did you experience, no, sorry, this one was answered.
No, that one we had before. That one we had before. Here's a nice one. Well, first of all, how does the view look like in space? Well, you've all seen pictures taken from space. The only analogy I can use, I've been to the Grand Canyon, I've been to the Himalayas. Before I went to either of these places, I've seen many pictures, and there are absolutely spectacular pictures of the Himalayas, spectacular pictures of the Grand Canyon. And yet, when you're standing at the bottom of the canyon and you're looking up at the walls and you see millions of years of geology and beautiful colors, there's just something about seeing it with your own eyes that is different. And on the other hand, there's many places that we can't go to, and the better, I'd love to see more VR coming back from Mars, for instance, so that we can share those experiences. As far as seeing stars and the sun and the moon and the earth at the same time, people ask about that. Can you see stars during the daytime? Generally, no. And the reason is that the sun is so bright. And of course, you're always looking through a window or through the visor of your space helmet. There's so much scattered light in that from the sun that it wipes out the stars. And also, since you're working in the daylight, your eyes are not dark adapted. But originally I was an astronomer, and I was always interested in seeing the stars from space. And so as an example, on the Hubble mission, after we finally deployed Hubble, for about a day, we were moving away from it, and we were doing it in such a way, in a constant attitude, so that one of our windows was always facing west. So it was actually, even after the sun rose on the east side of the shuttle, the west window was in a shadow. And if I put myself inside imagine an old photographer's hood, which I always flew with so that I could keep the light from the cabin from reflecting off the window. And I allowed myself to be dark adapted. And sure enough, there's a short period of time when, because we're so high, we're in the sunlight, but the earth below us is in darkness. You know, that's when after sunset, when you see the satellites flying over, that's what's happening. And so no light from the sun or reflected sunlight from the earth was hitting the window. And sure enough, even though the sun had risen, I could see the stars out the west window. As soon as we went over the terminator and the earth below us was bright, then there was so much reflected light in the window that the stars disappeared. So that's about it.
So before we wrap up, I think we could take one more question, and that is, what were the main differences between training in the pool and being in outer space for real, where you were trained?
Well, there are differences, and one of the reasons why they wanted experienced astronauts on Hubble was because there have been certain instances where people have been tricked, because water has viscosity. If you're free floating and you're holding on to a handrail with one arm in the water, you usually feel pretty stable, because the water prevents you from moving from side to side, but boy, you get up into space and you're holding on with one hand, and you can be flapping all over the place, and also when you're moving around large objects in the water tank, there's a lot of viscosity and drag, and so you have to push pretty hard. They actually, in order to give us training on what it would really feel like, part of our training we do on what they call an air bearing table, which is kind of like an air hockey, where we're floating on a cushion of air. And of course, we can only move around in 2 dimensions, but at least, and then they had the objects which we were going to be handling, which were, although they don't have any weight in space, they do have inertia and rotational moments of inertia as well. And so we could get used to moving them around and feeling that, you only fingertip pressure is all you need. You don't want to get things moving too fast or they'll get out of control. So yeah, you really do have to be careful not to get confused. And this is true about any simulator. It's true about the simulators we use for launch and landing the space shuttle. You have to understand the limitations of your simulator, and don't try to get more out of the simulator than it's capable of giving you, or you're in for some nasty surprises. We joke about being afraid. Mike Collins said it best. Were you ever afraid on your, you were the first Apollo 11 mission? He said, yeah, I was afraid I was going to screw up. Nobody wanted to be the person who was up there trying to fix Hubble and instead broke something. And you can imagine what was going through my mind when we might not be able to get the doors closed. Did I do something wrong? Luckily, I didn't, and we got them closed. But it's not being afraid of my life, it's being afraid of failure. And that's what training is all about. It gives us the confidence that when we run into problems, we at least have the best chance of, we don't panic. You learn to think about things coolly, come up with a recovery plan, and fix it if you can. And that's what we did.
I believe we have a few minutes. So just the last question to end with. Were there ever a moment you got overwhelmed?
Well, not overwhelmed so that I couldn't do my job. That would have been a very bad deal indeed. There was one moment, I have to say, it was on the second spacewalk where Tom and Kathy were out, and their job, we were going to roll up the solar arrays and remove them and bring them back to Earth and replace them with new arrays, which didn't have some of the problems that the old ones did. one of the arrays, the stiffening rod had buckled. I won't go into the details. They couldn't roll it up. It was a contingency we had thought about, and so they knew exactly what to do. They disconnected it. Kathy was on the end of the arm. She held on, and she just let go, and we fired the maneuvering jets of the shuttle and to move away from it. And this solar array then gradually started to somersault, and it was just mesmerizing. And we were all looking out the window. And after, I don't know how long it was, but this voice came out of the payload bay. It was Tom, who was there waiting for instruction. Hey guys, I thought we were supposed to be working. What am I supposed to do next? So that sort of shakes you out of your reverie. And that was, kind of, it was sure beautiful watching that. I could have watched it for hours, slowly moving away from us, but at some point you got to get back to work.
So that is all the time we have. And thank you all the participants for the questions, and handing it back to Jitu.
Everything has gone quiet.
Thank you, Professor.
Okay, I am going to have to go in about 3 minutes. Some of you may have heard in the introduction the other day, I'm the Deputy Principal Investigator of the MOXIE oxygen producing experiment on the Mars Perseverance rover. If things work out, I hope maybe I can give you a talk about that later in the summer session. But in any case, we have our weekly MOXIE meeting starting in about 2 minutes. So I'm going to have to say goodbye to all of you. It's been a pleasure. Thank you for your very perceptive and interesting questions. Good luck to the ISU students in the summer, and to the rest of you who are listening. Best wishes for your future careers and lives, and enjoy the summer. Bye-bye, everyone.
Thank you very much, Jeff. Have a good
one. And take care. Stay safe.